My name is John Pennycook, and I'm going to be talking today about our recent efforts to align the description of parallelism in SYCL and ISO C++. And this work started out as an attempt simply to unify some of the terminology used by the two specifications, but we ended up designing some interesting new SYCL features that we're now proposing as an extension. And I've tried to make this presentation more interesting than a big list of definitions, but some information has probably been lost in the process. So if you'd like more detail, then please read the paper. So how did we get here, and why are SYCL and C++ in need of alignment? Well, the first thing to note is that there are really three specifications that we need to pay attention to: SYCL, C++, and OpenCL. And these specifications have been evolving in parallel over the last 10 years or so, with SYCL drawing concepts from both C++ and OpenCL during that time. SYCL 1.2 combines C++11 concepts with OpenCL's ND range parallelism, allowing kernels to be written as lambda expressions. But note that SYCL 1.2 didn't adopt the full C++11 memory model because there was no way to map it to OpenCL 1.2 features. And you can see here that the C++11 memory model wasn't adopted in OpenCL until OpenCL 2. The next version of SYCL, SYCL 1.2.1, was just a minor release, adding support for C++14 features like generalized lambdas. And the most recent version of SYCL, SYCL 2020, was a major release. And as you can see, it pulled in a lot of new features. So aspects of OpenCL 2's memory model, like scopes, were combined with the C++17 memory model, and features like OpenCL subgroups and group functions were combined with the C++17 parallel algorithms to form SYCL's group algorithms. SYCL 2020 even pre-adopted some features from C++20, like atomic graph. But all three of these specifications continue to march forward, adding new features and clarifications with each new release. So maintaining alignment isn't something we can just do once. It requires constant and ongoing effort. But if we ultimately want to start seeing more arrows flowing back from SYCL to C++, that effort is necessary. Okay, so that's why alignment is important. But why did we decide to take a look at parallelism specifically? The code on this slide is a boiled down example of a real life use case, which attempts to synchronize all of the workgroups executing a kernel. And you can express this sort of synchronization using a combination of atomic operations and group barriers. So each workgroup elects one leader work item to synchronize with the leaders of the other workgroups, and all the other work items in the same group wait at a group barrier. And this code is syntactically valid, and it will compile with any existing SYCL compiler, but it isn't guaranteed to work anywhere because it makes two assumptions. The first assumption is that the leader of each workgroup makes progress while the other work items in the group wait at the second barrier. And this is probably a pretty safe assumption, but the SYCL 2020 specification doesn't really explain clearly how barriers are supposed to work, and I'll say more about that later. The second assumption is that every workgroup leader makes progress independently of all the other workgroups. And this assumption is definitely unsafe, because SYCL explicitly says that communication between workgroups is implementation defined. And it's important to note that this sort of synchronization has been explored in academic work before, and there's empirical evidence that the CUDA and OpenCL equivalents of this code do work some of the time on some GPUs. And CUDA has a cooperative launch feature specifically for enabling this use case. But what if we're not trying to synchronize all of the workgroups? What if we just want to synchronize some of the subgroups within the same workgroup, like in the code shown here? Well, this code still makes the same assumptions as the previous slide. It's just making those assumptions at a narrower scope, subgroup scope, instead of workgroup scope. And again, there's empirical evidence that this works on some GPUs at least some of the time. And there are some CUDA codes that employ this so-called warp specialization as an optimization. But this isn't necessarily guaranteed to work in SYCL. SYCL supports a wide range of hardware architectures, and the specification deliberately allows for subgroups to be implemented in different ways on those different architectures. Now, these problems aren't really SYCL specific, and the code snippets I've shown are written in SYCL, but the underlying questions about whether it's safe for different parallel workers to communicate or synchronize with one another are much broader than that. So let's take a quick look at how C++ addresses this issue. C++ defines three classes of threads of execution, each providing different forward progress guarantees. And the guarantees are described in terms of whether a thread eventually executes its first step and whether it continues to make progress after executing that first step. And I should say that what constitutes a step here is also defined by C++, and it includes things like library I/O and atomics. So a thread with concurrent forward progress guarantees eventually executes its first step and makes progress until it terminates. And you can think of this like an OS thread, and C++ strongly recommends that implementation create stood threads with these guarantees. A thread with parallel forward progress guarantees is not required to execute its first step, but once it does so, it effectively has concurrent forward progress guarantees. And you can think of this like a task in a queue. You can queue up many, many tasks, and the tasks that haven't started yet don't have any guarantees. Finally, a thread with weekly parallel forward progress guarantees effectively has no guarantees. And you can think of this a bit like a user level thread, like a fiber or a coroutine. If one thread in a process performs some blocking operation, there's no guarantee that the other threads in the same process will ever do anything. SYCL talks about forward progress guarantees too, but it does so using different terminology. And we should also bring in a third guarantee related to the assumptions that we saw earlier to describe whether progress is guaranteed at group barriers. And what the SYCL specification says is at the bottom of this slide. A SYCL implementation must execute work items concurrently and must ensure that the work items in a group obey the semantics of group barriers, but are not required to provide any additional forward progress guarantees. And the first thing to point out here is that concurrently doesn't mean with concurrent forward progress guarantees. It's really something more like at the same time. And this is a great example of why alignment between the two specifications is really important. So this wording in SYCL predates C++ 17, and it's actually based on similar wording that exists in OpenCL. But somebody more familiar with the C++ specification could easily read this description of work items and misinterpret what it means. Okay, so let's look at the different types of work items in SYCL and which of these guarantees they have. So in a basic non-ND range parallel for, SYCL is clear that no special forward progress guarantees are required. So we have a no for the first two rows. And basic parallel fors can't call barriers, so the third row just doesn't apply. In an ND range parallel for, the first two rows are also a no for the same reason. But whether we should have a yes or a no for the third row depends on what we think the semantics of group barriers means. And this is what I meant before when I said that SYCL isn't very clear about how barriers are supposed to work. But again, we can look to C++ for some guidance on how to solve this problem. And C++ defines a concept called blocking with forward progress guarantee delegation, which is used to describe the behavior of the C++ 17 parallel algorithms. And if we look at the code shown at the top of this slide, we have some thread calling a for each, and it's using a std par and seek execution policy. So let's assume that the calling thread is a std thread and that it has concurrent forward progress guarantees. The specification tells us that if the library creates any additional threads to help execute this algorithm, then those threads only have weekly parallel forward progress guarantees, and that comes from the par and seek execution policy. So if they've only got weekly parallel forward progress guarantees, how can we be sure that this algorithm completes, or in fact that it ever does anything at all? Well, this is where blocking with forward progress guarantee delegation comes in. When one thread blocks on the completion of a set of threads with weaker forward progress guarantees, at least one of those threads is temporarily strengthened to have the same forward progress guarantees as the blocking thread. So in our example, the std thread blocks on completion of the algorithm, and at least one of the threads executing the for each will be temporarily strengthened to have concurrent forward progress guarantees. And one way to think about this is as if the blocking thread is actually stepping through those weaker threads and executing them, as shown in this animation, but that isn't the only valid implementation. Okay, back to SYCL. If we take what we've learned from C++, then we can tighten the definitions in SYCL with two relatively simple fixes. First, if we say that all work items are threads of execution with weekly parallel forward progress guarantees, then that gives us the expected behavior in the first two rows. And this isn't really substantially different to the no forward progress guarantees wording that SYCL had before, but it's at least now using the same terminology as C++. Second, we can describe the behavior of barriers similarly to blocking with forward progress guarantee delegation. And the wording we went with was, when a work item arrives at a group barrier acting on group G, implementations must eventually select and potentially strengthen another work item in group G that has not yet arrived at the barrier. And this makes it clear what the semantics of group barriers are. And it also makes it clear that one of the assumptions from our motivating use cases was actually safe all along. So we can elect a work item to perform some operation on behalf of the rest of the group if the rest of the group is waiting at a barrier. But we still need to address our other assumption regarding the progress guarantees of work items in different work groups. Okay, so having established that work items are C++ threads of execution, it's natural to wonder what it might look like if somebody implemented SYCL on top of C++ threads. And the code on this slide is a very rough version of that, and we're deliberately ignoring the complexity of implementing barriers and some other complex SYCL features. But the basic idea is to use nested for each algorithms, with one algorithm for every level of the ND range parallelism hierarchy. So the outermost for each is associated with workgroup parallelism, and the innermost for each is associated with the work item parallelism within each workgroup. And a real implementation will probably have an intermediate for each for subgroups as well. Now, this is consistent with our view of work items as threads of execution, but it's important to note that work items in different work groups aren't guaranteed to be created at the same time because we have at least 2 different algorithm calls. And this suggests that we need to pay special attention to the hierarchy here and consider how to describe the forward progress guarantees of threads of execution that are created by nested parallelism. So our proposed solution is to adopt a new mental model for ND range parallelism, which maps very cleanly to this idea of a hierarchy of threads. And at the top of our hierarchy, we have one thread on the host, and then on the device side, we have a new concept called a root group, which contains all of the work items executing a specific kernel. And the host creates one thread of execution for this root group. The root group then creates one thread per work group. Each work group creates one thread per subgroup. And finally, each subgroup creates one thread per work item. And each thread blocks with forward progress guarantee delegation on its children. Now, because we have a hierarchy of threads, we can start to talk about what the forward progress guarantees are at each level of this hierarchy. But before we go any further, I want to stress that this is just a mental model. And so we're not suggesting that an implementation has to create a bunch of new hardware threads or that the behavior of existing SYCL implementations needs to change. In many implementations, I'd expect the root group, work group, and subgroup threads to not actually map to hardware threads at all or execute any code. But it's still useful to think of these conceptual threads as creating new threads at the next level of the hierarchy and then immediately blocking on their completion. To prove that this mental model is useful, we can look at how it would describe the behavior of SYCL applications running on various backends. And on this slide, we're showing the mapping to OpenCL1. So let's assume that our host thread is a stud thread that has concurrent forward progress guarantees. OpenCL1 says that individual work items have no progress guarantees, and we can describe that by defining every other layer of the hierarchy to have weekly parallel forward progress guarantees. Now, just like with our parallel algorithms example a few slides ago, we need a way to ensure that SYCL kernels running on OpenCL1 actually do something useful. And that's where reusing the concept of blocking with forward progress guarantee delegation can help us. So the host thread is blocking on the completion of the root group thread, so it will be temporarily strengthened and it can make progress. The root group thread, in turn, is blocking on the completion of a set of workgroup threads, so we know that at least one of those workgroups will be temporarily strengthened and can make progress. And this continues all the way down the hierarchy until we reach one of the work items. So we know that at any given point in time, at least one of our work items is making progress and our kernel is doing something. But we can't reason about which work items are executing because they all have weekly parallel forward progress guarantees. Well, what about OpenCL2? Well, one of the big changes in OpenCL2 is that implementations can choose to support a feature called subgroup independent forward progress. And when a device supports this capability, subgroups are said to make progress independently of the other subgroups in the same workgroup. And that guarantee holds even in the absence of workgroup barriers. And if we map that to our new mental model, the only change we have to make affects the subgroup level of the hierarchy. And where we previously had weekly parallel forward progress guarantees, we now have concurrent forward progress guarantees. So let's step through and see what that means. Well, as before, we have the host thread blocking on the root group thread, which in turn is blocking on a set of workgroup threads. But once a workgroup thread takes a step, it immediately creates its constituent subgroups, and these subgroups will continue to make progress until they terminate. And the work items within those subgroups still only have weekly parallel forward progress guarantees, as before. So there are 2 important takeaways from the last 2 slides. The first is that the correctness of SYCL programs is actually backend and device dependent. So the subgroup specialization example from the beginning of this presentation would be unsafe on OpenCL1 backends, but safe for some OpenCL2 backends, depending on whether they support subgroup independent forward progress. And the second takeaway is that our new mental model can succinctly describe the difference between these 2 backends using C++17 terminology. Right, we haven't had to expose this subgroup independent forward progress property from OpenCL to SYCL. And that should give us confidence that we're on the right track here. But we're still not done. Although we now have a framework for describing the behavior of different backends, in order to be really useful, we need a way to somehow expose these differences to developers. Otherwise, we've just designed a fancy way to describe implementation-defined behavior. So a lot of our previous work has involved what we call P3, balancing performance, portability, and productivity considerations. And often we're talking about this in terms of designing applications, but it applies to designing new SYCL features too. So the ideal is to design a feature that delivers great performance, that can be implemented across a wide range of hardware targets, and that developers find easy to understand and use. But what did we need to consider for this extension in particular? Well, first, it's critical that we don't change the default behavior of existing SYCL programs. We don't want code to suddenly stop working or to get slower unexpectedly when moving to a new version of SYCL. And that means that the default forward progress guarantee has to remain weakly parallel. We also need to allow for some flexibility if we want people to actually implement this extension. And that means accepting that not all devices will be capable of providing stronger guarantees. Some of them will continue to only be able to provide weakly parallel forward progress guarantees. But we still need to reduce uncertainty about whether certain code patterns are portable or not, so that developers can spend more time writing code and less time reading documentation and debugging. And that means providing some new mechanisms to query the forward progress guarantees that are supported by specific backends and devices. But it's important that when we introduce new queries, we make them as simple as possible, and we try to reuse existing query interfaces so that developers don't have to spend lots of time learning lots of new concepts. And then completely separate from the queries, we also need a clear way for developers to opt in to stronger forward progress guarantees when they think they need them. So a good example of this would be implementing an algorithm like a reduction or a scan, because those sorts of algorithms can be made more efficient if you can guarantee a small number of parallel workers with strong forward progress guarantees. And ultimately, we think the best path forward is to not force one solution on anybody. We need to accept that different applications have different requirements and that different architectures have different capabilities. And the developer of a SYCL application is the only person who can decide what the right balance of the three Ps is for their specific situation. So we need to give them features that empower them to make those decisions and balance those trade-offs. Okay, so what does our proposed extension actually look like? Well, this first example shows how we can use compile time properties, which are part of a different SYCL extension also developed at Intel, to declare the forward progress guarantees required by a specific kernel. And this get function with a special properties tag returns the requirements for this specific kernel functor. And because get is a member function, it's effectively part of the kernel definition. Right? So the requirements are embedded in the kernel, and whenever that kernel is launched, wherever it's launched, a SYCL implementation will be able to inspect these requirements and react to those requirements appropriately. And the property list itself simply describes the forward progress guarantees required at different levels of the hierarchy. And there's more detail in the paper about exactly how to spell out different kinds of requirements. But for the example on this slide, what we've got here says that we're requesting at least one work item in each work group created by the same root group must provide concurrent forward progress guarantees. So having defined the requirements for the kernel, we can now turn our attention to launching it. And as I mentioned on the previous slide, any requirements can be extracted automatically from the kernel definition. Developers don't need to use a special launch function or even remember which kernels require specific guarantees. They could just use a regular parallel for, pass in the kernel, and the runtime will do the right thing. And I should note at this point that it is technically possible for developers to provide a property list at launch time, so add a property list to the parallel for if that's what they want to do. And this is actually the only option if you have a kernel represented by a lambda expression instead of a kernel functor. But our recommendation is for developers to use kernel functors for these sorts of special kernels with special requirements because it helps to avoid mistakes. And you'll notice that I wrapped the kernel launch in a try catch here. This is because the extension allows implementations to throw an exception if the requirements requested by a developer cannot be satisfied. It's up to applications to decide what they want to do in this case, but we expect many codes will provide some sort of slower fallback path rather than aborting execution completely. So the code shown on the previous two slides is representative of what we expect most developers will write when they're using our extension. But the extension also includes some lower level queries for expert programmers. And the code shown on this slide is the sort of code we might expect to see inside a performance portability framework like Cocos or a library like 1DPL. And the first part of this example shows how to query the set of forward progress guarantees that a device can satisfy. And this query is kernel independent, and so it's something that a library could check at startup time to decide what sort of algorithms might be appropriate to use on this device. The second part of this example shows how to check if there are any implementation-specific limits that must be obeyed in order to satisfy the forward progress guarantees that have been requested. And so in this case, we're checking if there's a limit on the number of workgroups that can be launched, or if there's a limit on the size of those workgroups. And understanding these limits is particularly important if developers are trying to leverage strong forward progress guarantees for performance reasons. And that's because there might be a trade-off here. So weaker forward progress guarantees might actually be preferable if they allow for significantly more parallelism. Okay, so in summary, this work bridges the gap between SYCL and C++17 parallelism. By trying to align the terminology used by SYCL and C++17, we've been able to identify and fix several aspects of SYCL that were previously underdefined. We've also developed a new mental model for reasoning about forward progress guarantees in situations with hierarchical or nested parallelism, and we've shown how this mental model applies to the ND range parallelism in SYCL. And the final component of this work is our proposed extension, which adds new features allowing developers to explicitly state the assumptions that they're making, which might impact the portability of their kernels. As I said right at the beginning of this presentation, maintaining alignment between SYCL, C++, and OpenCL is going to require constant and ongoing effort. And now that we have a better understanding of forward progress guarantees in SYCL, we want to explore the interaction between ND range kernels and the STUD execution proposal, P2300, because that proposal defines concepts like schedulers with queryable forward progress guarantees. We also want to try and apply our learnings to other languages in this space, like OpenCL, SPIR-V, and Vulkan. And I want to end by highlighting that our extension is still just a proposal at this point, and there's a long path ahead of us if we want features like these to eventually make their way into SYCL or any other language. And we'd really appreciate feedback from the SYCL community to help us ensure that this extension is actually useful. So if you're an application developer, we want to know whether this would help you to write safer code, and whether the concepts make sense to you. And if you're an implementer, we want to know whether the concepts are descriptive enough to cover your hardware, and whether you think you could actually implement what we've outlined here. Either way, please get in touch, and thank you for your attention.